Why some changes in matter can be undone while others are permanent. For example, when ice melts into water, you can freeze it back again. But when a piece of wood burns, you can never get the wood back. This difference comes from two important concepts in science: physical changes and chemical changes. Understanding them helps us see why cutting paper is different from cooking an egg, and why freezing water is not the same as baking a cake. In this video, we'll explore these changes in detail, learn how to tell them apart, and see real-life examples that you encounter every day. Matter is the basic substance that makes up everything around us. If something occupies space and has mass, it is considered matter. The air we breathe, the water we drink, and even the chair we sit on are all forms of matter. Although matter can exist in many different forms, in everyday life it is mainly seen in three common states: solid, liquid, and gas. These states are not permanent because matter can change from one state to another depending on temperature and pressure. For example, water can be frozen into ice, melted into liquid, or boiled into steam, all without changing its chemical identity. This simple observation shows us that states of matter are not about what substance you have, but about how its particles are arranged and how much energy they possess. In a solid, the particles are packed tightly together in a very organized structure, often forming what is known as a lattice. These particles are not free to move around, but they vibrate slightly in place. Because of this, solids have both a definite shape and a definite volume. You can pick up a rock, an ice cube, or a piece of wood and notice that their shape doesn't change unless you forcefully cut, break, or melt them. The strong, attractive forces between the particles in a solid keep them in fixed positions, making solids rigid and hard to compress. Even when you heat a solid slightly, its temperature rises slowly because the energy mostly increases particle vibrations instead of changing its form. Some solids, like salt or sugar, are crystalline with orderly repeating patterns, while others, like glass or rubber, are amorphous, meaning they lack a regular structure. Liquids are different. The particles in a liquid are still close to one another, but they are not locked into fixed positions. Instead, they slide and roll past each other, which makes liquids flow easily. This explains why liquids have a definite volume, but no definite shape. If you pour water into a glass, it takes the shape of the glass. If you pour the same water into a bowl, it takes the bowl's shape. Despite this, the amount of water, or its volume, remains the same. Liquids cannot be compressed easily, since their particles are still quite close together. Another interesting property of liquids is surface tension, which makes water form droplets or allows certain insects to walk on water. Liquids also have varying viscosities, which is the measure of how thick or thin a liquid is. Honey flows slowly because it has a high viscosity, while water flows quickly because its viscosity is low. When liquids are heated, their particles move faster, and if enough heat is supplied, they eventually escape into the gaseous state. The gaseous state is the most free and energetic form of matter among the three. In a gas, the particles are very far apart compared to solids and liquids, and they move randomly in all directions at high speeds. Because the forces of attraction between particles are very weak in gases, they do not have a definite shape or a definite volume. A gas will always expand to fill the entire container it is placed in. This is why, if you open a perfume bottle, the scent spreads throughout the whole room. It diffuses rapidly due to the large gaps between particles and their constant motion. Gases are also highly compressible, because the particles are far apart and can be squeezed closer together under pressure. This principle is used in compressing natural gas into cylinders or in filling air tanks for scuba divers. The pressure of a gas results from the collisions of its particles with the walls of its container. When temperature increases, the particles move faster, and the pressure increases if the volume is kept constant. This is why hot air can cause a balloon to expand. Now, the most fascinating aspect of matter is that it can change from one state to another depending on temperature, and pressure. When you heat a solid, the particles gain energy, vibrate faster, and eventually break free from their fixed positions, turning into a liquid. This process is called melting. If you keep heating the liquid, the particles gain enough energy to completely overcome their attractions and spread out into the gaseous state, which is called vaporization or boiling. On the other hand, cooling reverses the process. A gas can lose energy and condense back into a liquid, and a liquid can freeze into a solid as its particles lose motion and settle into fixed positions. Sometimes, substances can skip the liquid state entirely. For example, dry ice, solid carbon dioxide, changes directly from a solid into a gas through sublimation, while frost forms when water vapor changes directly into solid ice through deposition. Another important concept is the energy exchange during phase changes. When a substance is melting or boiling, the temperature does not rise even though heat is being added. This is because the energy is being used to break the bonds between particles instead of raising their kinetic energy. This energy is called latent heat. For instance, when ice melts at 0 degrees Celsius, it remains at the same temperature until all of it has turned into liquid water. Similarly, boiling water stays at 100 degrees Celsius until all the liquid becomes vapor. This explains why boiling requires a lot more heat than melting, since vaporization involves completely separating particles, which takes much more energy than just loosening them in the liquid state. When comparing the three states, it is clear that solids are the most structured, liquids are more flexible, and gases are the most energetic. Solids are rigid with fixed shape and volume. Liquids flow with fixed volume but no shape, and gases expand freely with neither fixed shape nor volume. These differences are all due to how closely particles are arranged and how much energy they possess. In terms of density, solids are usually denser than liquids, and liquids are denser than gases. However, water is a famous exception because ice is less dense than liquid water, which is why ice floats on water, an unusual property that plays a vital role in supporting life on Earth. To sum it up, the states of matter explain how substances behave under different conditions of temperature and pressure. Solids remain rigid, liquids flow but stay together, and gases spread out to fill all available space. Changes between these states show us how energy and particle motion govern the properties of matter. While this chart introduces the three basic states, advanced science also studies other forms like plasma, found in stars and lightning, and exotic states like Bose-Einstein condensates, which occur only at extremely low temperatures. Understanding these fundamental states gives us the foundation for exploring all forms of matter in nature and technology. Matter is constantly undergoing changes all around us, but not all changes are the same. Some changes affect only the appearance, size, or state of a substance, while others completely transform it into something new. These two types of changes are called physical changes and chemical changes. Understanding the difference between them is very important in science because it tells us whether a material has simply been altered in form or whether it has been turned into a new substance altogether. A physical change is a change that affects the form, shape, or state of a substance without altering its internal molecular structure. In simpler words, during a physical change, the particles of matter remain the same and no new substance is formed. This type of change is usually reversible, meaning the material can return to its original state. For example, when you cut a piece of paper into smaller pieces, the paper is still paper. It hasn't changed chemically. Similarly, slicing bread, chopping wood, or painting a wall all count as physical changes. Even freezing water into ice or melting it back into liquid water are physical changes because the substance remains H2O in all forms. In each of these cases, the matter might look different or behave differently, but at the molecular level, nothing new has been created. On the other hand, A chemical change happens when the molecules of a substance rearrange themselves to form one or more entirely new substances with different properties. This kind of change is usually irreversible, which means once the change has happened, it cannot easily be undone. For example, when iron rusts, it reacts with oxygen and moisture to form iron oxide, a completely new substance. Cooking an egg is another clear example. Once heat changes the proteins in the egg, you cannot turn it back into its raw state. Burning wood is also a chemical change, as wood reacts with oxygen to form ash, smoke, and gases. Similarly, baking a cake involves mixing ingredients that chemically react in the oven to form something completely new, and rotting fruit like bananas undergoes a natural chemical breakdown that cannot be reversed. The key difference between the two lies in whether a new substance is produced. Physical changes do not create new substances, while chemical changes always result in new substances with new properties. For instance, when water boils, it simply changes from liquid to gas. But when sugar is heated until it burns, it breaks down and turns into black carbon and water vapor, new substances with very different properties from the original sugar. Another way to tell them apart is to look at energy changes and signs of reaction. Physical changes may involve energy, like heat absorbed when ice melts or released when water freezes, but they do not create new molecules. Chemical changes, however, often involve noticeable energy changes such as light, heat, or even sound being released. They may also produce bubbles, color changes, new smells, or solid deposits called precipitates. For example, fizzing when vinegar reacts with baking soda is a sign of a chemical change because a new gas, carbon dioxide, is being produced. In summary, physical changes are like rearranging the furniture in a room. You change how it looks, but it's still the same furniture. Chemical changes are like tearing down the walls and rebuilding the room into something completely different. You end up with a new structure altogether. Recognizing the difference helps us understand not only science in the lab, but also countless processes in daily life, from cooking and cleaning to rusting, burning, and freezing.